Good morning, everybody. Recent developments in zinc oxide based thin film gas sensors. My name is Uday Balegar. Introduction. Many gases are harmful for the sustainment of life on the earth. The reason is they could be toxic. Some of them are combustible and some are explosive. So, to solve this problem of toxic gases, we use gas sensors. A gas sensor is a transducer that produces an electronic signal. This article focuses only on zinc oxide based gas sensors. Among metal oxides, zinc oxide and tin oxides are most important and they have stood out the most in their versatile applications. First, let us consider the limitations of pure zinc oxide. Here, response and recovery times are relatively high. How to improve? To improve the sensor performance, either zinc oxide doped with other metal oxides or nano composites of two or more metal oxides with zinc oxide are prepared. For preparation of the nano composite, we will use many metals like titanium oxide, ferrous oxide, like that. Among them, tin oxides are abundantly used with the zinc oxide. Now let us consider gas sensor characteristics. Here, first characteristic is operating temperature. Here, what is the operating temperature? The temperature for which gas sensitivity is maximum. For many gas sensors, operating temperature is much higher than the room temperature. So, it is very difficult to conduct the experiments in normal room temperature. So, what to do? Efforts are bring the operating temperature to room temperature are being carried out. So, next characteristics is gas selectivity. Here, sensor may detect many gases simultaneously. Sensor must distinguish gases and should give signals for the required gases. Let us consider one of the main characteristics, response and recovery times. Here, what is response time? The time required to reach 90% of the maximum response of the gas from zero. That is known as response time. In the curve, we can observe the response time. What is recovery time? The time required to reach 10% from the maximum response in the absence of the gas is known as recovery time. For a better detector, response time should be as short as possible. We can quickly distinguish the gas. Let us consider recent developments in zinc oxide sensors. There are many studies in which they have fabricated zinc oxide, tin oxide, nanocomposite thin film gas sensors. In this case, conducted by A.S. Ismaila and the group, the mixed films of zinc oxide, tin oxide have better sensor characteristics. What is the reason behind this phenomena? Here, the porosity that created by zinc oxide into tin dioxide matrix. So, tin oxide and zinc oxide, they are ideal for heterojunction based devices. They have wide energy band gap, high sensitivity to humidity changes, and high thermal stability and non-toxicity. Next, in another study, thin films of zinc stannate and composite of zinc oxide, tin oxide, they have prepared. They have nanostructured perovskite with good crystallinity. Here, surface morphological study of zinc oxide, tin oxide using traveling electron microscope. What they observed? The average grain size ranges from 80 nanometer to 34 nanometer. The band gap energy samples in the range 3.9 electron volt to 4.13 electron volt from the ultraviolet to visible absorption spectra. And the sensitivity is increased to 48% with the increasing of mixing ratio of 60% tin oxide, ZS5. The sensitivity percentage arrives to 83% at 200 degrees Celsius. This improvement of sensitivity means hydrogen sulfide interact with the grains of the surface as well as with absorbed oxygen. So the dissociation of gas happens here. Next, let us consider the zinc oxide tin oxide nanocomposite study on the ethanol gas. In this case, nanocomposite thin films of tin oxide zinc oxide for 3 volume ratios in volume percentage of 30:70, 50:50 and 70:30 prepared and annealed at 500 degrees Celsius for 1 hour. And they carried the experiment with taking different gases. Gas sensing performance was determined. It is conducted using homemade static gas sensing system by exposure of LPG, carbon dioxide, hydrogen, ammonia, ethanol, chlorine and hydrogen sulfide. Among these gases, the nanocomposite thin film exhibited highest response and selectivity for ethanol gas. It exhibited the maximum sensitivity, sensitivity about 63% to the gas concentration at 600 ppm. In another study, let us consider variation in optical transmission. Zinc oxide tin oxide nanocomposite thin film in the range of 20.9 at percentage of 73.4 prepared by altering zinc and tin oxide zinc oxide atomic ratio in the starting solution. The average potential optical transmission increased from 70% to 95% within the visible range, 400 to 800 nanometer in the visible range as the substrate temperature increases. Here, as substrate temperature increased, the optical transmission also increased. It implies that the optical band gap for the films was determined to be in the range of 3.21 to 3.96 electron volt. And there is another study carried out by R.H. Burry. It is on the nitrogen dioxide gas sensitivity. Pure tin oxide and zinc oxide, percentage volume ratio is 5, doped with tin oxide thin film. Nitrogen dioxide gas sensing, the sensitivity is 1480 at operating temperature of 150 degrees Celsius with 100 ppm has occurred. Sensor structure showed the quick response of 3 seconds and fast recovery times of 10 seconds. Here, energy dispersive analysis of X-ray resulted that the thin film were non-stoichiometric in nature. Non-stoichiometric means the compounds or molecules, they need not be reacted with the whole numbers. The molecule, there may be fractions of the amount of the chemicals can be reacted with each other. Doping of zinc into tin oxide helped to enhance the response and selectivity towards nitrogen dioxide at 150 degrees Celsius. Let us consider perovskite zinc stannate. What are the research conducted? A perovskite zinc stannate thin film was prepared. Good sensing performances with a fast response time of 169 seconds and recovery time of 217 seconds on 80 ppm nitrogen dioxide exposure at room temperature was carried out and observed the result. Here, optical studies were carried, a higher transmittance, 85%, and a wide band gap energy, 3.5 electron volt, which is larger than that of zinc oxide tin oxide film. Next, the study on hydrogen gas sensing. Zinc oxide tin oxide thin film prepared on glass and porous silicon substrates at 400 degrees Celsius. The sensor response was estimated with 25% hydrogen sulfide gas for different temperatures. A sensitivity of 46% was observed on glass at room temperature for hydrogen sulfide gas, which was 3 times greater than single tin oxide gas sensor. Here, the higher sensitivity of mixed oxide is 92% on porous silicon at 200 degrees Celsius operating temperature with response time of 16 seconds and recovery time of 28 seconds, relatively, which is a better result. Next, there is a study on ethanol gas sensing. Mixed structure of zinc oxide nanorod on tin oxide thin film through the spray pyrolysis followed by thermal annealing was carried out. Here it is tested for ethanol, methane and hydrogen in air ambient for various gas concentrations ranging from 25 to 400 ppm. The film fabricated with molar ratio of zinc is to tin was 3:1 shows better sensitivity and selectivity to ethanol due to high sensing surface area of nanorod. When sensing surface area increases, automatically there will be more conduction and recovery and response time will be increased. So sensing efficiency also increases. Another study by Tarshika T and her group, it is on the ethanol gas sensing. Here the response to 25 ppm ethanol is found to be as high as 50 at 400 degrees Celsius temperature. The sensitivity of 1A08 is obtained for 50 ppm ethanol, which is nearly 15-fold higher than that of the response for methane and hydrogen at an operating temperature of 400 degrees Celsius. Let us consider the study on a zinc stannate thin film conducted by Patil and his group. Here, nitrogen dioxide sensors based on zinc stannate films. Here, scanning electron microscope and atomic force microscope studies shows that the film deposited at 400 degrees Celsius possess flax-like morphology and the voids present in the surface increases the roughness. When there will be a void, what happens? There will be more scope for the increase of the conduction. So automatically there will be sensitivity, higher sensitivity. Higher sensor response of 29.3 at moderately low temperature 200 degrees Celsius towards 40 ppm nitrogen concentration was observed. As low response time as 8 seconds and recovery time of 58 seconds are recorded for the sensor at its highest response. Lower detection limit achieved is 8 ppm nitrogen dioxide concentration at 200 degrees Celsius operating temperature. So it is the time to conclusions. Totally, the mixed films of zinc oxide, tin oxide have better sensor characteristics due to the porosity that created by zinc oxide into tin oxide matrix. The average optical transmission increased from 70% to 95% within the visible range as the substrate temperature increases. The improvement of the sensitivity means the gas under study interact with the grains of the surface of the thin film as well as with the absorbed oxygen. The doping of zinc into tin oxide helped to enhance the response and the selectivity towards different gases. Acknowledgements. The author is thankful to Dr. Raghu A., Research Supervisor and Assistant Professor, Government College, Mandya and Department of Physics, Government College, Mandya for useful discussion on this work. Thanks are due to him for providing laboratory facilities for this work. Thank Principal of the Institute for his administrative work support. Thank you.